Hello, in this worked example, we're going to be talking about the density operator. It's a quantum mechanical operator that is very useful in doing calculations of probabilities involving mixed states. And this worked example is meant as a complement to complement 8a in Beck, which treats the density operator and gives some examples. And we're going to generally follow what's done in that complement, but I'll provide some additional commentary and guidance to help you get you through what is an important but a little bit dense, if you'll forgive the pun, topic. And this worked example is also meant as a complement to the episode of What's the Big Idea involving Schrodinger's cat, in which we talked about pure states and mixed states. And as our sort of exemplar pure state, we considered a two-photon entangled state, which was a superposition, a sort of equally weighted superposition of the HH state and the VV state. And by contrast, we could have a state that was not a pure state, but an ensemble mixture of states, a mixed state, which instead of being a superposition state, was half the time our sample consisted of two photons in the HH state, and half the time our two photons consisted of a two-photon system in the VV state. And to date, most of your encounters in quantum mechanics have been with pure states of one sort or the other. Whoops. And when you're dealing with pure states and you want to calculate the probability of some event A, we have a well prescribed method of doing that. You calculate a probability amplitude, which is an inner product of the state A with the wave function psi, and then to find the probability, you take the absolute value squared of that probability amplitude. So that should be a very familiar thing to you. And then the question is, when you want to calculate probabilities when you're dealing with mixed states, what do you do? And that's where the density operator comes in. So when dealing with pure states, we define the density operator, we'll call it rho hat, is by definition just this combination, a ket and a bra. And taken together, this thing here acts as a quantum mechanical operator, the density operator. And then following the notation in Beck, we'd like to generalize this definition of the density operator to apply to the situation in which we're dealing with mixed states. And the natural way to generalize the definition is to define the density operator as now a weighted average of these psi's. So P sub j is this weighting factor, the percentage of, so to speak, of how much the mixture consists of each component state psi sub j. So this is the definition of the density operator when you're dealing with mixed states. So to take what is admittedly a very abstract set of definitions and make them a little bit more concrete, let's just write down the density operators for these two cases, for our two exemplar cases. So for the pure state, we'll write down the density operator corresponding to this particular psi. So all I've got to do is plug in for psi, plug in the ket, and plug in the corresponding bra. That's all I've done here. Here's the ket part, and this part here is the bra part, and that's just what the density operator is for this case. And then I can expand it out. I can just write it out as rho hat. Now, if you look, there's going to be a common factor of 1/2, which I can bring out. And then we have an H ket and the bra. There are going to be 4 terms here, so This is the first term, then the second term is going to go from here to here. So that's going to be a plus HH VV. And then the next two terms, there's going to be, it's going to come from here to here. So there's going to be a VVHH like that. And then finally, the last term is going to be this with this. So that's going to be a VV ket VV bra, close parentheses. So those are the four terms that we get for the density operator associated with the pure quantum mechanical state that looks like this. And then if you write down the density operator for the mixed case, that's actually a little bit simpler to write down. It's a 50-50 weighting. So in this case, the density operator is just 1/2 times H, comma, H, H, comma, H, plus 1/2 V, comma, V, V, comma, V, like that. So now there are only two terms. And you can clearly see that even though sort of superficially the pure states and the mixed states look like kinds of 50-50 weightings, you get a very different density operator between the two cases. And that's consistent with the fact that, as we showed when we did the what's the big idea for Schrodinger's cat, when you calculate probability amplitudes, and when you calculate probabilities, as we did in that what's the big idea, you get different answers for certain types of questions for these two states. And what the density operator really has to do with, it provides a more formal, systematic way for calculating probabilities. So the best way to show you what I'm talking about is by example. So let's do it. Well, before I can really show you how to use the density operator, there are a few preliminaries that we need to go through. And again, this is all in Beck Complement 8a, but let me summarize the key results here. So the first thing is to remind you what a matrix element is. That's something that should be familiar to you. But when we talk about matrix elements, by definition, you pick some basis, and if you've got some operator, any operator, which we'll call A hat, the matrix element A sub nm is defined. You pick a set of basis states to express the matrix in, and if the basis states are phi's, then by definition, the matrix element A sub nm is just this entity here. So this is how you calculate the matrix elements for any operator A. Okay, so that's preliminary point number one. And then once you've defined the matrix elements, you can define the trace associated with an operator. So the trace of any operator A is, by definition, the sum of the diagonal matrix elements, like so. And then a really important and useful result is that for any system, it could be a pure system or a mixed system, for any system which is represented with a density operator rho hat, if you go to calculate the expectation value of any operator associated with that system, you can calculate the expectation value of that operator just by taking the trace of a rho hat. Okay, so that's an important and very succinct result to write down, you need to think a little bit to make sure you understand what each of these symbols mean. And you should look to Beck complement 8a to see the proof of that. But that's an important result which we'll make use of in a moment, so I'm going to call that result number 1. And then a second important result, which again is kind of abstract, but it's easy to write down, is that for any operator that can be expressed in the form alpha, beta, a ket and a bra, if you go to calculate the trace of that operator, so the trace of alpha, beta, like that, you can show is just the inner product of beta with alpha. And let's call that result number 2, because we're going to make use of that in a moment also. So in this example, I'm going to take our sort of standard generic 2-photon experiment where we have polarization analyzers that can be adjusted to angles theta sub s and theta sub I. And we're going to ask what's the probability that the photons we get of the 2-photon pair, the signal photon comes out the top port, and the either photon also comes out the top port. But in this case, unlike previous cases, the system that we're going to study is going to be a mixed state. It's going to be half the time the 2-photon pair that we're feeding in to this system is in the HH state, and half of the time it's in the VV state. Now we just want to calculate this joint probability using this rather formal density operator method. So we pick a simple example just to make the calculation as transparent as possible. And to do this calculation, we're going to make use of the projection operator. So this entity here is the projection operator onto the state theta sub s comma theta sub I. And we're going to make use of the general fact that we can calculate this joint probability just by taking the expectation value of the projection operator. And now we're going to make use of the result that we called result 1 on the previous page, which said that the expectation value of any operator can be calculated by taking the trace of that operator times the density operator. So I'm just going to plug in. We have a situation where the operator that we're dealing with is this thing here, this projection operator, and the density operator is something that we just calculated. The density operator for the state we know is rho hat is equal to 1/2 H H H H plus 1/2 V V V V, like so. Okay, so bear with me now. This is going to get a little messy. So this joint probability that we're trying to calculate, the claim is I can calculate it by taking the trace of the operator that we're dealing with, which is this projection operator here. So I'm just going to plug that in. That's theta sub s comma theta sub I, the ket and the corresponding bra, like so. That whole thing times the density operator, which is, there's a factor of 1/2 H comma H H comma H plus 1/2 V, comma, V, V, comma, V, like so, and then close trace. And now I can rewrite this whole thing. There's a common factor of a half, which I'll pull out. And there's a identity which you can convince yourself is true is the trace of a sum is equal to the sum of the traces. So I'm going to write this as 1/2 times the trace of theta sub s, comma, theta sub I, theta sub s, comma, theta sub I, times h, the ket times the bra, like so, plus the trace. Whoops, I should have closed the first trace. And then the second trace is theta sub s, comma, theta sub I, like so. And now I've got a V, comma, V, V, comma, V, like so. And that's the end of my trace. And then this parentheses here matches this parentheses here. Okay, so that's a mouthful. And on the next transparency, on the next slide, okay, and now let me make use of the fact that these inner products here, this one here and this one here, are ones that we've previously evaluated. This inner product here is just going to be give us a cos theta sub s times cos theta sub I, and this one here is going to give a factor of sine theta sub s times sine theta sub I. So what this becomes then is equal to 1/2 times, and now I have a factor of cos theta sub s times cos theta sub I, times the trace of theta sub s, comma, theta sub I, h, comma, h, like so, plus sine theta sub s times sine theta sub I, times the trace of theta sub s, comma, theta sub I, the ket times the bra, v, comma, v, like so. And then I'll close my parentheses here. And now I want to make use of a result from a previous slide, which I said we're going to make use of, which is that if you have any operator of this form and you take the trace of it, it simply becomes an inner product. So we'll notice that these traces here are of this form, so I can replace the traces by a simple inner product. So what are we left with? We have that P of theta sub s, comma, theta sub I is equal to 1/2 times cosine theta sub I times cosine theta, whoops, back it up, theta sub s times cosine theta sub I. And now taking advantage of this relationship 2 here, I get simply an inner product of h, comma, h with theta sub s, comma, theta sub I. And then the next term here is a sine theta sub s times sine theta sub I times the inner product v, comma, v, theta s, comma, theta sub I. And these inner products are, again, we know the answers. They're just going to, this first one here is just going to give us another factor of cos theta sub s times cos theta sub I. And this one here is going to give us another factor of sine theta sub s times sine theta sub I. So at the end of the day, what do we got? We've got that this joint probability is equal to 1/2 times cosine squared theta sub s times cosine squared theta sub I plus sine squared theta sub s times sine squared theta sub I. Whew! Okay, so just to remind you, the question that we were answering was, this was our problem. We had our generic situation with um, a signal photon and idler photon, but now they were in this mixed state. And for the mixed state, we asked what's the joint probability of the signal photon coming out here and the idler photon coming out here. And here's the answer. For any values of theta sub s and theta sub I, we have an expression which tells us what this joint probability is. So just to check it for a simple case, let's imagine that we consider the simple case in which theta sub s is equal to plus 45 and theta sub I is also equal to plus 45. Okay, so we set both of the polarization analyzers to plus 45 degrees, and the joint probability then is 1/2 times, and the cosine of 45 degrees and the sine of 45 degrees is 1 over the square root of 2, and I'm going to have 4 factors of 1 over the square root of 2, so each term here is going to be a fourth, right? So the cosine squared 45 times cosine squared of 45 ends up giving a factor of fourth, and the same for sine squared of 45 times sine squared of 45. That's another factor, that's another 1/4, and I add 1/4 and 1/4, and I get 1/2, but I take a half of a half, and I get a fourth. So that tells you something that we actually are. I mentioned that this was true in the what's the big idea, and now we have a very formal way of telling that for this situation, 1/4 of the time, the signal and the idler photons are both going to come out the top port. And then you could use exactly the same method to calculate the probabilities for plus 45, say, and minus 45. And it's pretty easy to see because you're squaring everything. The fact that something's positive or negative doesn't end up making a difference. So this is also going to be a fourth, as is this one here, as is this one here. So there's sort of 4 possible combinations, and they're all equally likely when you have this 50-50 mixture of HH and VV. And that is probably not at all a surprising result, but we've calculated it rather formally using this density operator method. And the nice thing about the density operator method is that it can be extended and it can apply to much more complicated situations in which the results might not be so obvious. So that's it for this worked example. Hope to see you again soon. Bye-bye.